Hello, and welcome back to STEM Online Academy. My name is Jason, and we're going to get right to it today. Right? We're going to talk about why this logic mistake is actually ruining your calculus proofs, like your general calculus proofs. Okay, I'm going to explain why. Right? So, and it has to do with the quantifiers that you're using. Okay. So, what I mean by that is pretty much when you're doing calculus, more specifically analysis, you need to be very precise with what quantifiers you're using and what means what. That's what's really important. Okay. So let's get right to it. So I'm going to put something on the whiteboard here. Okay. Right. So let's just zoom in on the whiteboard. Okay. I'm going to show why this limit, right, is not a limit proof. Okay. So I'm going to write over here. So we're going to say that for every, just one sec. So for every x strictly greater than 0, there exists a delta greater than 0, and then this would imply that absolute value of x is strictly smaller than delta. Okay, this, all right, is not a limit proof. Okay, and it's not a limit proof for the main reason, the fact that when we're saying for all, okay, when we're saying for all x, we're saying that there's an arbitrarily small x greater than 0. Okay, that's what it's saying right here, right? We have an arbitrarily small x greater than 0, and this is not true. How can it be true if you have an arbitrarily small x greater than 0? And with a delta greater than 0, implying that this arbitrarily small x has to be strictly smaller than delta, where delta is greater than 0. That doesn't make any sense, right? If you understand the implication of that meaning right there. Okay, so it's very important to be able to analyze what you're writing down, if it makes sense or not. Okay, so this is not a limit proof. Right? This is not a limit proof. That's the main problem. Okay, why this is not limit proof. Now the struggle, students will actually students will know calculus but not know logic. Yes, yet they think that since they know calculus that they're good at math. You're not good at math. You're not good at math if you don't understand logic. And it's not just for calculus, for anything. Mathematics is mathematics in general. It's embedded in the rules of logic. The foundations is logic. So if you don't understand logic, you don't understand mathematics, right? So you can know calculus, but I mean, what I mean by that? Firstly, our system has made all of us think that if we're good at computing some basic limit, memorizing our derivative formulas, that somehow that we are now really good at calculus, and more importantly that we can generalize and say that we're good at math. That's much further from the truth. That is not true at all. Okay, so I'm here to clarify that that does not mean that you are mathematically inclined. Okay, so and it's a major disservice from our system, our school boards, and our even universities to continue this cycling of somehow making students or whoever think that somehow that they're going to be good at mathematics because they can remember formulas. That's nonsense. Okay, so let's get during this video you're going to see why or why what I'm saying is very true, especially for new viewers. If you haven't seen these quantifiers before, and you're taking or about to take a math course or are in a math course that doesn't, you know, reveal you to this, you may need to rethink, oh, am I really good at math? Do I understand the implications? You're going to see what I mean. Okay. So what does for all and there exists really, really mean? Okay. So let's go to our whiteboard here. Okay. So the for all quantifier, okay, the for all quantifier I'm going to underline is this guy, right? That's my for all quantifier. Okay. That's what a for all quantifier is. And there exists quantifier is on the right here that I've highlighted, right? The reverse E, that's an exist quantifier. So the for all, right? The for all quantifier, right? You only make sure you use that symbol when you're using the for all in any of your math classes, okay? For all means a statement, right? Is going to be true for every item in a group, right? Every item in a group, until there is something that makes it, at least, that makes it false. Okay. So otherwise, the statement is true for every item in the group. Okay. That's what a for all quantifier is. Right. So true for every item in a group, unless we find something that's going to make it false. Okay. Now the there exists quantifier on the right here that I keep highlighting in red, the reverse E, if you haven't seen this before, that reveals, okay, that reveals something interesting. Okay, the there exists quantifier means that we have a statement, okay, statement that is said to be true for, now be careful, for at least one item in the group. Okay, make sure you understand that. So a statement is true. A statement is true for at least one item in the group. Okay, so at least one item in the group has to be true. That's there exists quantifier. Now again, the for all quantifier means that a statement is true for every item in the group, unless we find at least one item that makes it false. Okay. So I hope you understand. I hope that makes sense, right? So for all means a statement is true for every single item in the group, right? Until there's one item that's going to make it false, whereas there exists quantifier on the right hand side here, okay, the reverse E is this quantifier, means that we have a statement is true for at least one item in the group. The rest can be false. The rest can be all falses in our our truth or false analogy, if you want to say. Okay, so I hope that is making sense. Now another question we need to ask ourselves is why for every x greater than 0 and there exists delta, and then there exists a delta greater than 0, implies that the absolute value of x is less than delta, delta misses the point. I'm talking about this now. Right? I'm going to highlight. Why does this statement here, this is supposed to be an epsilon delta statement, why it misses the point? Okay, so why does what I highlighted in blue miss the point? It misses the point, right? Because again, first off, the notation is wrong. There shouldn't be an x, there should be an epsilon, right? Next to that for all quantifier, right? If you put an epsilon instead of the x there, it should be for every epsilon greater than 0, there exists a delta greater than 0, implies that the absolute value of x is all in delta, right? That would be correct. What we have here misses the point because we are looking at an arbitrarily small x, okay, was greater than 0, right? But if you look at an arbitrarily small x, right? If you look at a graph, for instance, just give me a second here. Just give me a moment. If we have a graph, I'm going to zoom in, right? We have a graph here, right? Maybe something like this. and you have your x, right? Your x-axis, your y-axis. Sorry for that. Your x is right here. Just give me a second. X and y-axis. Well, on the y-axis, this can be partitioned into a rectangle. Just give me a sec. And this strip of the rectangle, right, is saying that we have a distance between x and a, right? So x and a. Second here is black. So let's see this distance between the yellow part, the upper part, and the lower part here. There's a distance of x minus a, right? Distance between x minus a. If we have that distance, there's an arbitrarily small increment difference between x and a, right? But we can't have that for all x, right? If we have for all x greater than 0, okay, this is not logically coherent, okay? All right. So this is already a problematic structure that we have, right? That misses the point. In reality, it should be saying for every epsilon, right? It should be saying that for all epsilon greater than 0, there's a delta greater than 0, implying x is smaller than delta. Okay. Right. So that's going to be the correct structure. So the correct structure, right, would have actually been this. This is the correct structure. I put an arrow. Is that for every epsilon greater than 0, there exists a delta greater than 0, implying that x value, and to be more specific, be careful, 0 is something smaller than the absolute value of x, something smaller than delta. Okay, that would have been a correct structure of a limit proof. All right. Now, how can we use my systems technique to do this correctly, right? Remember, for those of you who don't know, I do mathematics by using a systems technique to simplify things, okay? And that is visualize. Okay, just give me a sec here. So it's systems technique. Systems technique. Technique. And it is one, you want to visualize. Right? Then the next part, that's step 1. Step 2 is to model. Step 3 is to, you want to be able to execute. And then you want to be able to verify. Okay. And this system that I use, it won't always work 100%, right? If it was that, then we'd be solving all the math problems on the planet and we'd probably win the Millennium Prize. No, it doesn't work that way. But it can give you a structure in your mind of how to progressively deduce things logically, step by step, and have your thinking in much more order. Okay. All right. So try to apply the systems technique wherever is needed. Okay. It's a very handy technique. Right. Now, next on the list, how does this fix the epsilon delta confusion? How does it fix the epsilon delta confusion? That's what you have to ask yourself. What's the relevance to this? Well, as you can see here in my graph there, okay, I wanted to make a graph of this. Well, the graph is some function, okay? So let's just say, just give me a sec. let's just say, for instance, okay, so we had a function here. That graph was a function that I was using. It can be any function, y equals f of x, provided that it's continuous and needs to be continuous. Otherwise, this epsilon, this limit deficit doesn't make any sense. It has to be continuous. So I drew a continuous function like y equals x cubed of some sort. So I wanted to see if this statement made sense by visualizing a function. So I drew a function y equals f of x. Then I said to myself, well, so that's the visualization stage. We did the visualization stage. Okay, that's visualize, step one. Then you want to model. What it means by model is not necessarily to have a geometric model or picture, but it means to have a schematic or some sort of schematic, some sort of schematic or linguistic framework of what you're saying is true or false. Okay, so they gave us a linguistic um, statement here, but we can see based off the graph it wouldn't make sense that for all x greater than 0, there's just a delta greater than 0, implying absolute value of x has to be smaller than delta, right? Because if there was an x strictly greater than 0, that would mean, what would that mean? Right? Well, that would mean that we would have an x, all positive x values, but can we have all positive x values if your x has to be, if your absolute value of x has to be strictly less than delta? Can you, where delta has to be greater than 0? Not necessarily, because then the graph, right? If we zoom in on the graph here, okay, this graph, then first off, what I have here, I made a mistake. Sorry, this happens. This graph here, that little partition there is the f of x minus L part of the epsilon delta, right? So f of x minus L significantly smaller than epsilon. That's this portion here. The x minus a minus x minus a smaller than delta, or the x smaller than delta, is this portion. Let's put that over here. The x minus a. So let's look at this portion here. Let's say this whole thing is the x-axis. Okay, we know it's the x-axis. Now, if that's the x-axis, all right, and let's say this is 1 point x1. Let's say this is x, right? x1, and this point here is a. So this is a, and this is x1. Let me get rid of that. I can get rid of it. Yeah. So this one here. Okay, just 1 second. So as you can see, this is point A and this is point x1. I've made a vertical rectangle. If I take the distance between these guys here, right, from here to here, from the 2 points, then this would leave me with x minus a, right? That's the difference. That's how we get the distance, right? Which is equal to some distance d, let's say, for distance. Now, in our statement, it said that a is 0, right? Because it said that absolute value of x has to be strictly smaller than delta. So if a is 0, then my rectangle gets incredibly small. My vertical rectangle gets incredibly small, right? So if a equals 0, well, this implies that I'm getting absolute value of x small. Absolute value of x is my distance, right? But if the absolute value of x is my distance, right, then that wouldn't make any sense, because there should be a sort of a rectangle. There should be a rectangle that takes 1 point x to another point a, right? A separation distance between point x and point a. These vertical lines here define a distance. Without that, that already is going to be problematic, right? If x is the distance, I'm saying what distance? right? It doesn't make any sense. Okay. So that alone already tells you something is fishy with this definition here, right? This x is strictly smaller than delta. Okay. So there's a number of things that are making it sound off. Okay. So we did the model, and then you want to execute. Well, to execute in this case, you're just going to take that statement and modify it. You need to modify because you already know there's something wrong with it. Okay. Now, it helps if you had some sort of introduction to logic, a logic class, because then you can figure out if this is making sense or not. Well, if you don't, if you've seen the definition of an epsilon delta, then you'll know that you need to maybe place some things around. So there should be an epsilon in place of x, right? So for every epsilon greater than 0, because it's the epsilon that's incredibly small. And what I mean by the epsilon is this guy here, okay? For that f of x minus L, right? Where f of x, right? F of x is y, so that's why it's on the y-axis, okay? This portion here, let's say up to some point f of x, okay? Say this point is f of, let's say this point is L. L is the limit, okay? The limit that we're dealing with. So that's L. This is L. Let's say this is f of x. And they are separated away for some distance, epsilon, okay? And it's an incredibly small distance. So f of x minus L has to be strictly small. Then epsilon, that rectangle there that I am talking about, okay? Right there, right, has to be arbitrarily small. So that epsilon has to be strictly greater than 0, okay? All right? But if epsilon is strictly greater, so epsilon has to be strictly greater than 0 because there's some separation distance. Otherwise, it doesn't make sense. So for every epsilon greater than 0, there exists a delta greater than 0, okay? Which implies absolute value of x has to be strictly greater than 0. And that's another thing too, strictly greater than 0, and x has to be smaller than delta. With what I said earlier, if you had the x minus a, if a is 0, then we just have x is the distance. If x is the distance, well, what's stopping x being, okay, yeah, x can be positive here, right, on this axis, right? If this rectangle, right, if that rectangle gets incredibly small, right, okay, it can still be positive. But, and then you just have that vertical line. But if that x was over here, let's say, right, there's some vertical line here, then this x has to be strictly less than 0 because on the negative axis. But if x is strictly less than 0, that's in violation of the limit definition. That's why it doesn't make sense in general, right? So where x has to be, absolute value of x has to be strictly less than delta, because if x is negative is less than delta, but delta is greater than 0. But then at the same time, it's supposed to be for all x greater than 0, unless we can find one x not being greater than 0, then something doesn't make sense here. Okay, so that's the argument, right? So we used my systems technique to modify this craziness over here. Okay, all right. So that's what I wanted to mention. All right. So why this is the case. Now, finally, one last thing I want to talk about is why this is important and why I wrote my book. So we have a major crisis in our hands. I don't know if anyone knows, in education. And that crisis is the fact that we are not teaching or preparing students to think in a rigorous and logical manner. We are spoon feeding them nonsense in schools. And when I mean nonsense, I mean absolutely, totally nonsense. The high school curriculum is completely like garbage. It's not helping students progress and to go to university. And even if they do go to university, they're not, quite often they don't do well. They're not able to sustain sustain a certain level of competency in at least STEM courses, especially like calculus and yeah, calculus courses, physics courses, all these things. So there's a major crisis because we've dumbified everything, and that's why I wrote my book Axioms for that reason. Now, it, it is a hard book. It's a no nonsense introduction to mathematical logic. Okay, and it will help students at least in grade 12. I think that's who it's appropriate for. If you're in grade 12, you should read this book. It's going to help make that transition, especially if you're a STEM. If you're a high school student who plans to go on a STEM course, I don't mean business, they don't need it, or any of these other psychology courses, you don't need this book. But if you're in a STEM course, you want to go into STEM in university, read this book. Okay, it will be an excellent transition from the high school, right? From high school to university level um, mathematics courses, because in STEM you have to take mathematics courses, no way around it. Okay, and what it's going to give you is it's going to give you an understanding of how things work. It just amazes me that somehow that we have students in university who don't have, forget logic. They don't even have the common sense to figure out some basic things. And they say they're in STEM and they say they plan to be engineers or whatever. Okay. So reading something like this is going to discipline your mind to think in a structured, logical way, not just for the math per se. That's not the point. The point is to think in a logical way in your everyday life, in university, so you can hopefully become successful. And yes, it's excellent preparation. It's excellent preparation to the reality of STEM courses. Okay, I'm very proud of this book, and it took me a while to make, but trust me, it's well worth it. Okay, it's available as an ebook, actually, not paperback right now, but ebook. So if you are interested, just let me know. There'll be a link below where you can get it. Right. So finally, today was one of these days where I just come on and I just talk in general or show my face. I like to connect with you guys. It means a lot. So if you're struggling, if you're struggling with the concepts of calculus, you can uh, always get my free PDF when it comes to the systems technique that I've highlighted down here. Okay, the visualize model, execute, verify. It's completely free. It's going to show you where you can what to look for in problems. There's certain problems that keep coming up again and again. I'm sure you can see patterns in your courses. Certain problems where you can utilize this systems technique, and it's very powerful. Okay, so there's a free PDF there. As I said, my book Axioms is available. That's why I wanted to take up this specific concept today, because a lot of you are missing. Pretty much, let me put it this way: you know the calculus formulas, but you don't know you don't understand it, and you don't understand it. You don't understand logic though when it comes to math. Okay, that's where my book comes into play. Okay, is to understand logic in general. All right, and so my book Axioms will be available, or if you're having trouble with your course, like more specifically, and you need an extra hand, I provide coaching services. Uh, Again, uh, my services are online. Doesn't matter. I'm in Ottawa, Ontario, but mainly online, please, because that's how I get my clients from everywhere. So online services, we can do problems. I can break down the problems in a very systematic way, so you will be able to understand even the hardest problems. All right. So coaching is available. All right. That is it. I gotta get going. Like and subscribe. It's always a pleasure, guys. And I will see you in the next video. Have a great day.